I guess my hidden dream, ambition, was to participate in the development of a drug that could be useful for the health.
Welcome to the Greener Grass podcast from BlueBird Botanicals. I'm your host, Lex Pelger. Today is one of the highlights of my career as a journalist and drug writer. At the Pueblo Cannabis Research Conference, I got to sit down with Dr. Vincenzo Di Marzo. He is a research director at the Institute of Biomolecular Chemistry in Naples, Italy. And he's one of the world's leaders in cannabinoid research. He's written over 450 peer-reviewed articles, and his review papers on the endocannabinoids are some of the most poetic writing I've ever seen in an academic journal. But it's not only in the field of cannabinoids where Dr. Di Marzo shines. As a chemist, in the fields of pharmacology and toxicology, he was the most cited author in 2010. This makes him one of the most outstanding leaders in the field of chemistry, and he happens to be focused on these cannabinoids that we all find so fascinating. But as our audio engineer Matt Payne points out, this show requires more careful listening than some. It's a focus on deep science, and so I'll give a little bit of background to try to help make it more clear. Dr. Di Marzo studies the endocannabinoid system. This system was discovered in the early 90s. Just like the morphine derived from the opium plant helped us discover our own endorphin system to control pain, the cannabinoids from the cannabis plant helped us to discover this widespread human signaling system that's used for homeostasis and balance around the body. The first receptors found were called CB1 and CB2. CB1 is found over many of the higher levels of the human brain, and the CB2 receptor is found on all the organs in the body. Soon after that, they found a neurotransmitter that was a cannabinoid. It was named anandamide after the Sanskrit word for bliss. These are endogenous cannabinoids, as in they are cannabinoids made by the human body and used in a wide array of functions, from energy balance to the immune system, as well as reproduction, learning, and motor control. So the endogenous cannabinoids are made within us. The phytocannabinoids are the ones made by the plant. Of course, the most famous of these are THC and CBD, but many dozens of other phytocannabinoids are made in the cannabis plant. The term for how these are created is called their biosynthetic pathway. Molecules have to be assembled by a cell, just like a car has to be assembled on a production line. So in the plant, the CBG is made first, and then it can either be converted into THC or CBD. That's the biosynthetic pathway within the plant. How the cannabinoids are made in the human body is quite complicated, but we're learning more each and every year about the biosynthesis of these molecules within us. The last two things I mentioned are pharmaceutical in nature. Back in 2006, a drug was approved in Europe called Rimnabant. It was a drug that blocked the action of the CB1 receptor, effectively doing the opposite of what THC does. That meant it helped people suppress their appetite, and that's what it was approved for in Europe. It actually wasn't approved by the United States Food and Drug Administration because they wanted to see more data, and it turns out that they made the right call there. Because after the drug was on the market, researchers realized that it also increased suicidal ideation in some of its users, and therefore the pharmaceutical drug had to be pulled. This is part of the reason that the pharmaceutical industry is still leery of cannabinoids in general because of early missteps like this. It's not only because of the history of cannabinoids in this country is so politically charged. It's also because the lawyers who run most of the big pharmaceutical companies don't want to take a risk on a field that's had a couple of missteps in its past. However, things are starting to change. Just this week, something very big happened. The U.S. Food and Drug Administration approved a drug called Epidiolex. What is special about this drug is that it's the first cannabinoid drug where the ingredients actually come from the plant instead of the laboratory. It's a mixture of THC and CBD made by a company called GW Pharmaceuticals. It was just approved this week, and it heralds a bright future as we return to the power of cannabinoids for health. So I hope this outline helps illuminate this show, and I hope you enjoyed listening to Dr. Di Marzo as much as I did. This show is brought to you by BlueBird Botanicals, to spread education about cannabis and other things on the greener side of life. BlueBird CBD oil comes from farms in southern Colorado and is grown using only water, soil, and sunlight. Go to bluebirdbotanicals.com for more info. Hello, everybody. We are very happy to be here with Dr. Di Marzo, who just finished giving his speech here at the Pueblo Cannabinoid Science Conference. And so before we got into more about your work, I just wanted to ask, so you started with a chemistry undergraduate at the University of Naples. Did you always know that chemistry was going to be your future?
Actually not. I mean, when I was a small child, like many others, I used to play with the little chemists. But my real dream was to study the chemistry of life. So that was in the 60s when I was a little child, and then in the 70s I went to school, and in the 80s I went to the university. And unfortunately in Naples, there hadn't been introduced yet the faculty of biochemistry or chemical biology, as they say. So I studied chemistry. I liked chemistry, but I actually went into chemistry because I wanted to do biochemistry. So I did 3 years. At those times, there was no doctorate, PhD system in Italy yet. I was 83, 84. So I studied, actually it was 78. I'm much older than I would like to think. So I started in 78. There was only chemistry. And then you did 3 years of pure chemistry. And then the second 2 years were which was equivalent to a master. You would either do industrial chemistry, inorganic chemistry, organic chemistry, and within organic chemistry, which I choose, you could do, finally, after 3 years and a half, I could start working on biochemistry. So I actually wanted to do biochemistry.
And it just wasn't developed at the time?
It was developed, but in Italy, I think chemists are a bit more conservative. Biochemistry was more left in the hand of the biologists and the medical doctors. So you would find good courses in biochemistry, in biology, but particularly in medicine, which I wanted to look at the chemistry of life from the chemistry point of view, not from the medical point of view. And then I did my doctoral thesis in Naples, and then I did my PhD in biochemistry at Imperial College in London, where I was also introduced to the pharmacology, so molecular pharmacology. So I did a PhD in biochemistry and molecular pharmacology in London. I stayed there for almost 4 years.
Are you glad now that you did get that background in chemistry?
Absolutely.
Now that you're dealing with so many molecules?
Absolutely, yes. Because I don't want to underrate other disciplines, but obviously from the chemical background, you can actually understand many things. You like going into depth into why not only cells work and how they work, but also how drugs work. I guess my hidden ambition was to participate in the development of a drug that could be useful for the health of people. So that's why I then immediately moved from biochemistry to molecular pharmacology. So I'm glad, yes. I think it still gives me a different perspective.
And then in that field, went on to the lipid biochemistry and natural products chemistry. Why lipids when there's such a complicated, difficult system of fats to discover?
Exactly because of that. Because they were considered, just like a source of energy, and not even the best one. The annoying one, the one that accumulates, the one that gives you the bad shapes. So no, lipids actually, we always thought, and I always thought that if there are so many, if the cell is surrounded by lipids, it must be using lipids to communicate with other cells. And maybe if the cell contains so many different types of membranes that are made of lipids, maybe lipids are also used to communicate within the cell, so for inter and intracellular communication. And those were the years when actually old lipid signals were being discovered. So a few Nobel Prizes were given for the discovery, for example, of prostaglandins, leukotrienes. So I worked in a lab at Imperial College where they did the chemical the identification of the leukotrienes, which are these lipid signals coming from arachidonic acid, which are responsible for some asthma responses, bronchoconstriction, and so on and so forth. It used to be called, in a very unprecise manner, slow reacting substance of anaphylaxis, and later on was discovered in the lab where I was, not by me, but a few years before I get there, as being made of leukotrienes.
What did it feel like in your career to watch lipids become such a central force and realize these are a very important messaging system?
Well, I was very happy because I always believed in lipids in that way. And obviously, this actually explains why I started working on endocannabinoids, because endocannabinoids like leukotrienes. I did my PhD thesis on leukotrienes. So endocannabinoids were similar to leukotrienes. They were derived from arachidonic acid, which is an omega-6 fatty acid, long-chain fatty acid. It's very important for your brain function, but for many other things. But like many other things, it could also be bad for you. So this is what was really something that in lipids attracted me. The idea, the challenge that studying lipids, a single lipid by itself, you can never tell whether it's doing something or the opposite of that something, because it can be transformed. It's part of a long pathway of signals and can be transformed into another signal that can act on another antenna, another aerial, another receptor that has a completely different function.
It must make your life very complicated.
No, but it's quite nice.
And how did you come up with the term endocannabinoids?
Well, it was quite obvious. I never thought it was a great idea, and then I discovered that everybody was using it. So I thought, well, maybe I should have patented it. But it came from endorphins. So endocannabinoids didn't work. Endorphins worked quite well because morphine, it only lacked a letter. So I thought it had to be endocannabinoids, even though it's a long one. But everybody started using it. Some people actually still uses endogenous cannabinoids. And this is, to answer your first question, why, and I get upset when they use endogenous cannabinoids, because endocannabinoids are not endogenous cannabinoids. And endogenous cannabinoids are when you smoke a joint. So some of those cannabinoids stayed inside you, and they're endogenous cannabinoids. Endocannabinoids are a different chemical entity, as Meshulam discovered. So they must be given a different name.
And you did a lot of work, including getting into the Human Frontier Science program, looking at the biosynthesis and the metabolism and the structure-activity relationships of anandamide.
I see you went very far in.
I read all of your review papers.
Yes. Yeah, that was a very fortunate thing to do, because it really started up my career. In Italy, it's not easy to get funding. In those times, we were at the beginning of the 1990s. Things were still doable, but this is a type of research that needs money, and that kind of money is not already at that time was not easily available for a young person. So that grant really started me up. It was a good grant, difficult to get. I was the PI together with the two US groups and the Japanese one. So it was really a crucial point of my career.
And can you talk a little bit about the synthesis pathways of anandamide and how many there are and how confusing that can be?
Yeah, that's the part of the story. When I finished my PhD, I went back to Italy, and so I became a permanent researcher there. And after a couple of years, anandamide was discovered by Meshulam, and I got a phone call from another Italian guy working abroad in Paris, Daniele Piomelli, who is still working in the US, in Irvine. And so he nicely proposed to me if we worked on that together. And so immediately, the aim was to identify the biosynthetic pathway. And it was clear that anandamide was chemically similar to other compounds whose biosynthetic pathways had already been studied back in the 70s. So basically, our job was to demonstrate that the same pathway was also used for anandamide. And that was difficult. I don't want to go into the technicalities, but the problem was that anandamide comes from arachidonic acid. And that pathway uses fatty acids that are not normally, it uses fatty acids that are normally found on the SN1 position of phospholipids, where you find very little arachidonic acid, but you find a lot of palmitic acid, stearic acid, oleic acid. So obviously, people was not much in favor of this idea that the same pathway could also be used for anandamide. We had to struggle a little bit, but in the end, we demonstrated that actually uses the same pathway as oleoyl ethanolamide, palmityl ethanolamide, and this is why anandamide has much lower amounts in tissues than all the others, because it uses arachidonic acid coming from the SN1 position of phospholipids, and that's very little compared to other fatty acids. And this is also why the other endocannabinoid is much more abundant, because it comes from a biosynthetic pathway that uses the SN2 position, the 2 position of phospholipids, where you find a lot of arachidonic acid. In fact, arachidonic acid is the most abundant fatty acid on the 2 position of phospholipids. So I hope this is more or less clear, but if you want, I can make you a drawing for your next book.
And is that the reason some people are thinking that 2-AG might be more of the lipid to be looking at?
Yeah.
That there's more going on with that than there might be with anandamide?
Yeah. Initially, it was like that. Something else happened in the US. It was discovered that 2-AG could be a retrograde signal to control neurotransmitter release, and definitely 2-AG can do that better than anandamide, but not because it's more abundant. In fact, what we measure, it's probably 99%. What we measure of 2-AG is 99% being used as an intermediate in the metabolism of phospholipids and triglycerides in different tissues. Only a little part of 2-AG is being used to activate cannabinoid receptors. If it wasn't like that, we would be in a permanent high all the time, because it's 100 times more abundant than anandamide and 10 times more abundant than it takes to fully activate the CB1 receptor. So we definitely think that not all of it is being used for that purpose.
And for that reverse neuronal signaling, it's one of the first early things that we found out. But you were also instrumental in pulling in the metabolic idea of how much the endocannabinoids are involved with metabolism in the body. Can you talk about how you figured out this was an area you wanted to move forward in?
It was actually because after a few years spent in Italy, I was a bit fed up. I wanted to leave Italy to work on endocannabinoids, but in a different environment. So I went to Richmond, Virginia. And I started, I moved from molecular pharmacology to real in vivo animal pharmacology, which I'd never done as a chemist before. So I was given the responsibility of 2 small groups by 2 very important scientists in the field. One was the late Billy Martin, who was the dean of pharmacology and toxicology at Richmond University. And with him, we did some important, nice studies to demonstrate that anandamide, in fact, does not only activate CB1 receptors, and that's another difference between anandamide and 2-AG. But I also met there with George Kunos, who was actually working. He had started only a few years before on endocannabinoids, but he was very much interested in the relationship between endocannabinoids and leptin. So that was a very fortunate meeting, because we could demonstrate together that leptin was an anorexigenic hormone, possibly acts by inhibiting the biosynthesis of endocannabinoids in the hypothalamus, and this is probably one of the reasons why leptin is anorexigenic. And from then, I had also done some work with another group in England to show that, in fact, the levels of endocannabinoids in the hypothalamus go up following food deprivation and go down following food consumption, which fits with the idea of leptin inhibiting them. So that really gave us the idea that endocannabinoids could be the ideal orexigenic intermediates between the action of some hormones like leptin, peripheral hormones like leptin in the brain. And that was also found for ghrelin, which is another hormone with opposite action. So leptin, it induces food intake. So from then on, and then came rimonabant, and we got involved in the study of the mechanism of action of rimonabant, which is a blocker of CB1 receptors, and we could demonstrate that in fact rimonabant could reduce body weight and things like insulin resistance, glucose intolerance, because it was also acting on peripheral action. So I think my major contribution to that field was to point out that CB1 receptors were not only important in the brain, but also in peripheral tissues to control metabolism.
And speaking of the rimonabant, how do you feel now, because that caused such a backlash in industry against cannabinoid research and closed up so many good operations? How do you feel now about where the field's moving and the relation between cannabinoids and the pharmaceutical players?
Yeah, you're right. First there was the stigma against the THC and the agonist of CB1 receptors. Now the stigma against the antagonist. I think the pharmaceutical industry gets too easily scared of these things. They should be a bit more brave. And there were all the signals to demonstrate that, in fact, even rimonabant should have been used at much lower doses. But I think the companies at those time wanted to go for the magic pill, the one that would allow you to eat what you wanted without becoming obese. It was a dream, and that would have been, a blockbuster drug, of course. Industry wants to make a lot of money, but rimonabant could have been used at a lower dose and without probably much effect on body weight, on body appearance, but a lot of beneficial actions on obesity-related metabolic disorders that are not so visible, but are the ones that are actually killing you in the end. So it's not obesity itself that kills you, but its consequences on the cardiovascular system. So we actually had evidence that by blocking CB1 receptors only in the periphery, or by reducing the dose of rimonabant in a way that it would preferentially act in the periphery, we could have had a safe drug. And unfortunately, we didn't manage to pass that message on time. And then many scientists, including George Kounos, were involved in developing peripherally restricted CB1 antagonists. But again, the pharmaceutical industry doesn't seem to be. It's maybe now there is a stigma on that, and they don't seem to be willing to pursue that. So I'm now pursuing other kind of more dietary interventions like the omega-6, the omega-3 fatty acids, fish oils, krill oils, but also the microbiome role.
And that was one I'd like to hear more about, just because everybody's so excited by the microbiome these days, but it's so complicated, and the endocannabinoid system is so complicated.
They go well together.
What is it like for you looking at the nexus of those two mysterious fields?
Yeah, I've actually just started, so I'm still a beginning on the gut microbiome. But it takes more or less the same techniques. So a bit more of metagenomics, perhaps, because it's the number of genes involved. There are so many-fold higher. It's so many orders of magnitude higher than our own genome. And the number of species, the number of families of bacteria, and it's not just bacteria, it's yeast, it's viruses, it's so many things. So it's very complicated, but it can be dealt with by the metagenomics, the bioinformatics approaches, and various metabolomics and transcriptomics techniques that we now have, and we didn't have only 10, 20 years ago. So many things are possible also in terms of personalized medicine. So we can do these things, and I think the endocannabinoid system and the endocannabinoidome, which is much larger than the endocannabinoid system, can play a role in the way the gut microbiome affects health, both in a positive and in a negative way.
Mm-hmm. And speaking of the pharmaceutical research, you work with GW as well.
Yes, I've been collaborating with them since almost the beginning, since they got interested in, since they got this, ambition of making a drug out of cannabis. Nobody had managed before, out of a cannabis extract. We had THC, Nabilone, of course, with very restricted use because of the side effects. But so they were very ambitious. And they wanted to develop it as a drug, not as a supplement or as a food additive. So basically, I must say that I feel honored to have collaborated with them, because it helped us also for our research. Not only because they provided some research grants, but also because it opened up a little bit my mind. I was probably over-focused on the endocannabinoid system and THC myself. I never thought about the other phytocannabinoids, which can be as important, if not more important. So working with them has been beneficial for research in general, for my research in particular. And I think we've done good things together.
What about pushback from people in the community who are concerned about things like Epidiolex coming in and perhaps pushing more lo-fi methods out?
I don't think the two things should be seen in competition. People should be informed that maybe they can treat themselves, or their doctor can treat them using non-approved drug approaches. There is many of them, or approaches that are approved but are not fully understood. Just think about acupuncture, for example. It seems to be working so well, but we still don't know how it works. So I don't think it's the choice of the patient. I, as a pharmacologist, I would always prefer to be treated with something that I know how it works, or at least I know to some extent how it works, that I know that it's always the same. So I go to the pharmacy, I go to the drugstore, and I always, if I want to buy it, I always buy the same thing. I always take it in the same way. So I don't criticize those that don't think the same way as I do. This is the way I was trained as a scientist, as a researcher. This is the way I think things should be done, but sometimes you cannot wait for the development. Speaking about Epidiolex, I think that there is lots of good results with cannabis oils, CBD-rich extracts or CBD-enriched oils, but there is also some variability. So you don't know what they're taking, and in some cases there might be too much THC for a brain, for the developing brain to tolerate. Because at this meeting we've been hearing that THC is not bad for you, it's not toxic, it's not it's never killed anybody. But this is probably true for adults, and this is true for THC, obviously not for synthetic cannabinoids, but for children. So we're talking about an indication which is for children. And I wouldn't want to give THC or anything that interferes with the natural action of CB1 receptors in the brain to a child whose brain is still not fully developed. So I think having a drug in that particular case is probably much better. So but if people want to keep on using more or less controlled cannabis extracts, it's their choice.
Yeah, I think that's mainly the fear out there.
I don't
is
think
that there's going to be some kind of...
There is not going to be competition.
Or monopoly on it.
Especially if Epidiolex is reimbursable. If it is approved, when it is approved, it will become also reimbursable because it's going to be for a minority of patients.
And in the filing data there, I was intrigued by the amount of work they wanted to see on the liver and liver safety for Epidiolex.
That's part of the protocol. It's for all drugs. Liver function needs to be tested for all drugs. Again, developing a drug can take 10-15 years, lots of money, lots of investments. So the companies, of course, they probably develop 1 out of 100 compounds that they find. They want to make at least some money, some profit, and you can understand that these kind of drugs become when they are approved, eventually they can become quite expensive. But on the other hand, we're talking about orphan drugs, orphan indications. So obviously, the liver, usually the toxicological studies are done in adults for obvious ethical issues. So if it's safe in human adults, should be also safe for children. But this is part of the protocol. You have to test all the possible toxicological, even though it's everybody says cannabidiol is a safe drug. It's been given up to a gram and a half a day. These things for drugs to be approved by the FDA and to be sold as therapeutic drugs following clinical trials, they need to be done.
Especially with
it's part of the regulations.
Mm-hmm. And it seems, especially with the interactions with the CYP enzymes in the liver and how much that changes. Were there any concerns for you in terms of what the processing of other drugs?
I don't know the data, but some people actually suggested that the reason why it's so efficacious is because it improves on other drugs that are being co-administered, in as much as it inhibits their inactivation by the cytochrome P450 enzymes. I don't know. Honestly, I don't know. It's still not known what is the exact mechanism of action of these compounds. And it doesn't require to the FDA to know exactly the mechanism of action, as long as it's safe and it's efficacious, and it's saving life, because it is, such a drug, if it was ever approved, shown to be safe, it would save hundreds of children, thousands of children.
And so, one last question before I let you go. What are the fields that you're most excited about coming up now in cannabinoid chemistry and pharmacology? What are you really keeping your eye on?
The ones I'm working on. No, I'm really keen on investigating these interactions between the endocannabinoidome, the phytocannabinoidome, and the gut microbiome. I think again the gut microbiome is something that's been overlooked for many years, or associated only to a limited number of disorders. I think it has to do more than in inflammatory bowel disorders or obesity. It has probably to do the dysbiosis, the disruption of the healthy gut microbiome has to do probably even with more with other disorders, even going up to the brain, I think. So we want to study it from the molecular point of view to see whether what are the molecules that are produced by the gut microbiome. So I view it as a going back to the old times of cannabis research. So I always wanted to rationalize. People at this meeting probably will not be so much in agreement with me. Rationalize the use of cannabis by understanding how its major bioactive components are working. So THC via the endocannabinoid system, the other phytocannabinoids via the enlarged endocannabinoid system and other endogenous systems, but without negating the use of a cannabis extract, any cannabis extract. I mean, I would like to understand how a cannabis extract works. I wanted to understand how a cannabis extract works, and now I want to understand. People are talking about fecal transplants. So a fecal transplant is something that's probably much less, I would say, pleasant than at least, even though it can be quite pleasant, than smoking a joint. But still, it's quite, it's an approach that you really don't understand if it works. You cannot predict if it works, when it will work, on whom it will work, and why it works. So we want to identify what are the chemicals in the fecal transplant, which are already working for a limited number of disorders, exactly as it was for cannabis at the beginning. So I see it like, transposing my experience with the cannabinoids to the microbiome as a very exciting, possibly final turn of my career.
Excellent. Well, we wish you the best of luck in that.
Thank you very much. It was very nice questions.
Good talking to you. Thank you. Greener Grass is a BlueBird Botanicals podcast. Their CBD oil supports a healthy body and a strong endocannabinoid system. They've got friendly customer service who can answer any of your questions, and the number is right there at the top of their webpage. But, per the FDA, they won't be able to make any medical claims for these nutritional supplements. That's also the reason you'll hear little about CBD on this show. There's no need for us to add more evidence about CBD when a simple Google search will give you more than you can read in a month of Sundays. So this show covers the cannabis world and more with editorial freedom from BlueBird Botanicals. Thanks for joining the Greener Grass podcast. As always, our audio alchemist is Matt Payne. The Gypsy Jazz theme music comes from Brett Van Donsel. Our beautiful bird sounds are courtesy of Lang Elliott. And I'm your host, Lex Pelger, wishing you a bright green day.